Snell's law describes the behavior of light when it goes from one medium into another of different density, and there's a change in the speed. And it basically goes like this. Now, they do insist on this for a pair of given media. So you could be talking about air to glass, glass to perspex, or something like that. But for a pair of media, the sine of the angle of incidence is directly proportional to the sine of the angle of refraction. They will also accept you saying that the sine of the angle of incidence divided by the sine of the angle of refraction is constant. They will accept that version of it. They then give you a little diagram of a glass block, and they're going to use this to see if Snell's law is correct. And they fire in a ray of light here. It goes towards the normal when it's in the block because it slows down, and then goes away from the normal when it exits. Now, they haven't drawn the diagram very accurately, because if this is an exactly parallel-sided block, which you assume it is, then the original path direction should be absolutely parallel to the ray when it finally comes out. So I drew a line carrying on, and then you can see that that ray there is not quite parallel to that. It should be come over to the right a little bit. Anyway, you've got to use this diagram and use the angles to show that the refractive index of the glass is 1.51. So what I'm going to do is go for the light entering the block, and this is the angle of incidence, this is the angle of refraction, so I've got to divide the sine of that by the sine of that. And the question is, how big is that? Now, I've marked it in a 60, but why is it 60? Well, if that is parallel with that, and that's 60, that must be 30, and because that is parallel with that, you can almost see what's going to happen. If that's 60, you'll find that that's 60 as well, and that's 30. Well, all you've got to do then is to say, well, this refractive index is sine I over sine R, and it's sine 60 over sine 35, 1.51. So quite a simple exercise. It then goes on to talk about monochromatic light. So this is light of one wavelength, and it's going through a section of an optical fibre. And as you remember, optical fibres consist of a core and then cladding. This will be a certain type of glass and then a different type of glass on the outside. The refractive index of the cladding material has to be less than the refractive index of the core. And the reason for that is you want total internal reflection to take place. The speed of light here must be slower than the speed of light there. And if that is the case, you have the chance of total internal reflection. Well, it turns out, if you do the mathematics, that the refractive index, yes, it's the sine I over sine R, but it's also equal to the ratio of the speeds of light. Now, when I write down a refractive index, I'm going to say which medium I'm going from and where I'm going to. So if you talk about the refractive index of the core, the assumption is you're going from air into the core. In other words, you are doing what that ray of light does. And what we're going to do is work out the speed of light in the core. Well, if we start off with that relationship, working out the speed of light in the core is easy. It's simply the speed of light in air divided by the refractive index of air going towards the core. Now, when we say the speed of light in air, technically it's the speed of light in a vacuum, but we take the two as being the same. So speed of light in air, 3 times 10 to the 8, 1.51, we know that's the index for the air to the core, and you get a slowing down process, as you would expect, 1.99 times 10 to the 8 meters per second. But then they say, well, what is the index for the light going from the core to the cladding? Now, the approach I'm going to take with this one is this. If I want to go from the core to the cladding, that should be given by, yes, it's sine I over sine R, but it's also the speed of light in the core divided by the speed of light in the cladding. No, I've just worked out what the speed of light in the core is. It was the 1.99 times 10 to the 8. So all I've got to do is work out the speed of light in the cladding and then divide one by the other. And you can get the speed of light in the cladding very easily. It's the speed of light in air divided by the speed of light in the cladding there. So the speed of light in the cladding it's the same procedure as last time, and it's a bit bigger than the previous one, 2.07 times 10 to the 8. Now that is what we were expecting. The speed of light here is slower than the speed of light there. So here it's 1.99 times 10 to the 8, and here it's 2.07 times 10 to the 8. Well, that's the hard work done. The index is speed of light in core divided by speed of light in cladding, 0.96. And that's the answer that they're looking for.